band. Okay. Looks like we are, in fact, live. So, stop playing around with pens and instead start talking about bond polarity. So this builds on other stuff we've already discussed. Bond polarity, electronegativity. Recall that electronegativity, one of the trends you already had to learn, is the attraction of an atom for the shared electrons of a chemical bond. So, the greater the electronegativity of something is, the more it pulls on the electrons in the bond, meaning you get unequal sharing. So here we have a chlorine molecule. Oops, that's not what I wanted. Yeah, there we go. Let's bring up the periodic table. Molecule of chlorine means 2 chlorine atoms. Every atom of chlorine has 17 protons, 17 electrons. So this molecule of chlorine has 34 protons, 34 electrons. The whole thing is electrically neutral. Because these electrons are shared perfectly evenly between the two atoms, they spend half their time over here and half their time over here. The result is that each chlorine still has, on average, 17 electrons. 17 electrons, 17 protons, electrically neutral, electrically neutral. Okay. Then we look over here at B, we have hydrogen chloride. These guys do not have the same electronegativity. Chlorine is more electronegative than hydrogen is. So 1 proton, excuse me, 1 proton, 1 electron from hydrogen, 17 protons, 17 electrons from chlorine, total of 18 protons, 18 electrons. The whole thing is still electrically neutral. But these electrons are no longer evenly shared. They spend more time on chlorine than they do on hydrogen. Therefore, chlorine has, on average, somewhere between 17 and 18 electrons. Hydrogen has, on average, somewhere between 0 and 1 electron. So that means that hydrogen has a positive charge. 1 proton less than 1 electron. And chlorine has a negative charge. 17 protons, somewhere between 17 and 18 electrons. It's not a complete separation of charge, though, so we can't just say positive and negative. Okay, that's why we use these swoopy-looking D things. The D, in this case, means partial. It's a partial positive charge over here on hydrogen and a partial negative charge over here on chlorine. There is a charge separation. This makes it a polar bond. It has 2 poles, a positive pole and a negative pole, sort of like a magnet has a north pole and a south pole. Opening my soda, hold on, and taking a sip. So that makes this not just a polar bond, we also call it a dipole because it has 2 poles. A magnet is always a dipole, always has a north pole and a south pole. If you were to break a magnet in half, then you would have 2 magnets, each with a north pole and a south pole. But with electrical charge, you can get what's called a monopole. You can have an ion by itself, a positive ion or a negative ion. We call this a dipole because you have 2 poles that are bound together. Now, if you increase the electronegativity difference between your atoms, eventually you get over here on the right an ionic bond. Chlorine is so much more electronegative than sodium that chlorine is able to just completely steal an electron from sodium, thus giving you a positive ion on sodium and negative ion in chlorine. All right. So, we can put this in terms of numbers. Okay? You look at the difference in electronegativity between your 2 elements, between the 2 atoms. Okay? All the way over on this end of your scale, 0 difference. 2 atoms of the same element. Okay? In this case, 2 atoms of chlorine. They both have the exact same electronegativity, so the difference between them is 0. From a difference of 0 to a difference of 0.4, we have a nonpolar bond. Okay. At that low difference in electronegativity, there just isn't enough difference for the more electronegative atom to get an unequal share. It's like somebody who wants it a little bit, somebody who wants it a little bit more, but not enough more to really raise a stink about it. A difference between 0.4 and 1.7 gives you a polar bond. It's still a covalent bond. The electrons are still being shared, but they're not equally shared. They are more on one atom than they are on the other, giving you a partial positive on one side, a partial negative on the other. Once you get above 1.7, that's when you get a complete transfer of electrons. The more electronegative element is able to just completely steal electrons from the less electronegative element. Okay, let me make sure people can hear me. Yes, people can hear me. Good. I've made that mistake before. There we go. All right. So what if you don't have numbers? That's easy enough. We have simple rule of thumb for that. If you have a metal plus a nonmetal, that's going to get you an ionic bond. If you have two different nonmetals, okay, that is to say they're both over on the right-hand side of the periodic table, over here in the green section on ptable.com. In that case, oops, that's not what I wanted. This is what I wanted. In that case, you have a polar covalent bond. Okay, they're sharing their electrons, but they are not sharing them equally. If you have two of the same nonmetal, like if they're both hydrogen or both chlorine or something, then it is a nonpolar bond. The exception, and one that you have to know, is carbon and hydrogen. Carbon and hydrogen are close enough in electronegativity that we call it a nonpolar bond. Okay, that goes to this region of this chart right here. Hydrogen and chlorine are down here in the nonpolar region. Okay. And of course, don't waste cheese. Cheese is perfectly nice. All right. So these are some different ways that we can represent this distribution of charge, this unequal sharing of electrons. We have our little swoopy Ds that we've already seen. Here we have chloromethane, CH3Cl. Carbon is less electronegative than chlorine. Chlorine is more electronegative, so you have a partial negative charge on chlorine, a partial positive charge on hydrogen. This over here, it represents the dipole moment. Remember, a dipole means we have two poles. The moment just means the size and direction of the dipole, where the charges are, how big those charges are, and how far apart they are. That's something you can actually calculate with more information. You don't have to worry too much about that. You are going to have to be able to draw these arrows. They're very simple. They point toward the negative end of the dipole, and they have a little cross down at the positive end to look like a plus sign. Okay. So in this case, carbon is positive, chlorine is negative, so it points from carbon over to chlorine. We see that again over here on methanol. Methanol, or wood alcohol, is poisonous. Be very careful with it. Don't drink it. It'll make you go blind and then kill you. It's why you should be very careful about drinking moonshine. Moonshine is just some random guy's liquor that he made in his garage, and it could have a lot of methanol in it. All right, so here we have carbon bound to oxygen. Oxygen is way more electronegative than carbon, so it's also more electronegative than hydrogen. So you get a partial positive on hydrogen, partial positive on carbon, and a partial negative on oxygen. So because we have more than one place where we hit this charge separation, we draw multiple arrows. We draw the arrow pointing from hydrogen toward oxygen, a little plus sign over on the hydrogen end, and we have another arrow pointing from carbon over to oxygen. Okay. So that indicates that oxygen is negative, carbon is positive, hydrogen is positive. You can do this for bigger molecules with multiple charge separations. So down here at the bottom, Oh, Wesley, I don't think you're going to fit here at the moment, especially not with your big goofy cone around your head. I'm sorry, buddy. All right, so down here we have a polypeptide. That is to say, a part of a protein, amino acids. So here we have the amino end of one protein, or of one amino acid, and the acid end of another one, and the peptide bond between them. This here is the carbon of that. Oh, my dog is being very cute. You have the carbon of this bond is going to be very positive. The oxygen is going to be very negative. And thus you get a partial positive on carbon, partial negative on oxygen. Meanwhile, over here, nitrogen is more electronegative than hydrogen, so you get a partial positive on hydrogen, partial negative on nitrogen. Here, we have a partial positive on carbon because nitrogen is also more electronegative than carbon. So the nitrogen is pulling electrons from this carbon over here, and this carbon over here, and this hydrogen. Thus, it is fairly electronegative. This carbon is in the same boat as this carbon over here on the left, and thus it is positive, it is negative. Here we have another nitrogen. It's also going to be negative, just like this guy is, and so on. Then over here on the right, we have a comparison between water and methane. Methane is CH4, that's cow burps. The carbon-hydrogen bond is nonpolar. And we contrast that with water, where the oxygen-hydrogen bond is very polar. So each hydrogen here is positive, this hydrogen here is positive, and oxygen is negative. Thus, the water molecule is strongly polar. Okay, that's what this picture down here represents. It's showing the distribution of electrons. It's showing the density of electrons running around the water molecule. So we have a lower density down here on the hydrogens, it's positive, and we have a higher density up here on the oxygens, it's negative. Meanwhile, methane is made of nonpolar bonds, and thus it is completely nonpolar. We have a perfectly uniform distribution of electrons. Okay, we don't see any differences on this big blobby molecule. Okay. Now, you can also get polar bonds adding and subtracting. So let me show you that with water really quick. So, water, we have oxygen bound to hydrogen atoms. Then we have our two lone pairs. Now, here is one arrow pointing from hydrogen to oxygen. Here's the other arrow pointing from hydrogen to oxygen. Now, when you look at, you're a little bit inconvenient at the moment, Mr. Sasha. I know you want to play. You want to participate in whatever game I'm playing up here. Please don't step on the keyboard either. Let's... No, I don't want to remove the capture device. Okay. All right, so the thing about these is that they both point up, but one is pointing to the right, one is pointing to the left. So when you look at the molecule as a whole, you add these two arrows together. The rightward portion of this one perfectly balances out the left portion of this one because the two hydrogens are exactly the same. But they both point up, so that doesn't cancel out. So when you look at the whole molecule, you get this. So that will give us our segue into talking about polar molecules, which is really important for talking about talking about chemical properties, physical properties of different materials. The fact that water is polar has a huge impact on its behavior. It explains why water is a liquid, and we look over here, methane is a gas. They are both about the same size. Water has a molar mass, remember that from the first test, 18 grams per mole. Methane has a molar mass of 16 grams per mole. Okay? If they're about the same size, you would expect them to have about the same melting and boiling points. But water doesn't boil until 100 degrees Celsius, 370 Kelvin. Meanwhile, methane boils at well below the freezing point of water. It's like negative 80 degrees Celsius, I think. I'm coming up with that off the top of my head. Don't take it as gospel. But water's incredibly, ridiculously high boiling point, melting and boiling points, compared to other similarly sized molecules, is due to the fact that it is very, very polar, which leads to other properties, which we may get to later. But for now, that is it for this particular set of slides. You need to know about polarity. You should have already talked about that in lab, so I won't go into it here too much. I just wanted to talk about polar bonds. But polar molecules was covered in the labs when we talked about molecular geometries and Lewis structures, so not going into that here. But I will now end this particular video. I'll be coming back in about 5 minutes to go over nomenclature, binary covalent nomenclature. See you in a few.